Next, we're going to talk about systems of linear equations. So what do I mean by that? I just mean multiple equations that all use the same variables. So here's an example. We can write a set of three equations as x1 plus 2x2 plus 3x3 equals 6. Second equation, 2x1 plus 4x2 plus 6x3 equals 10. And the third equation, 3x1 plus 3x2 plus 3x3 equals 9. So there's three equations, and there's three variables, x1 and x2, that appear in each of the equations. Now, using our matrix notation, we can write these three equations in matrix form like this. So what I want you to do is you could pause the video and write out the matrix multiplications and show that you get the same set of equations like this. Okay. Now, a common question when you're working with system of equations is, does this set of equations have a solution? And if it does have a solution, how many does it have? So what I mean by that is, can you find an x1, an x2, and x3 such that these three equations are true? Sometimes you won't be able to find such an x1, x2, x3. Sometimes you will be able to find one. And sometimes there are multiple choices of x1 and x2 and x3. In fact, infinitely many choices. So a set of equations will fall into one of three categories. It can either have no solution, exactly one solution, or infinitely many solutions. If it doesn't have a solution, we say it's inconsistent. And if it does have at least one solution, we say it's consistent. Now, if we look at the above equations, we can see that they are inconsistent. They do not have a solution. So let's see why. If we take the matrix form and write it out like this, we have the first column times, so the first column is 1, 2, 3, second column is 2, 4, 3, third column is 3, 6, 3. The left side of the equation is 1, 2, 3 times x1 plus 2, 4, 6 times x2 plus 3, 6, 3 times x3. Now we can factor some things out. So this is the same 1, 2, 3 times x1 plus 1, 2, 3 times 2 times x2. I'm just factoring out a 2 from this vector. Plus 1, 2, 1 times 3x3. And now you can see that the first element is 1 in each of these. So this expression becomes this, x1 plus 2x2 plus 3x3. The second element is always 2, so this becomes 2 times x1 plus 2x2 plus 3x3. And let's ignore the last one for a second here. Now what this means is that if I look at the first, if I pick any x1, x2, x3, the second entry is going to be twice the value of the first entry, because the dependence on x1, x2 is x3 is the same in the first two entries, except in the second one you multiply the first one by 2. So in other words, the second entry is always going to be twice the value of the first entry, no matter which x1, x2, and x3 you plug in. Now if we look back at the right side of the equation, the second entry is 10 and the first entry is 6. So on the right side of the equation, the second entry is not twice the first entry, and therefore this system of equations does not have a solution. Now you can't always tell just by looking at an equation whether it's going to have a solution or not. So we have a theorem here that tells us exactly when a system of equations is going to have a solution and when it's not going to have a solution. And here's how the theorem works. A system of equation, A, which is an n by p matrix, times x, which is a p by 1 vector, equals y, which has to be an n by 1 vector, is consistent if and only if the rank of A equals the rank of the matrix A with the column Y appended on the end of it. So I call that an augmented matrix. So what this says is the statement that AX equals Y has a solution is equivalent to the statement that the rank of A equals the rank of AY. All right, so why is this the right test for whether a system of equations has a solution? If you take the matrix A and you append Y onto the last column, this says that if the rank is not increased, then it will have a solution. So if you append Y on the end and it does not increase the rank, that means Y is not linearly independent, or in other words, is linearly dependent on the columns of A. And therefore there exists an x, x1 to xp, such that a1, x1, so a1 is the first column, x is some coefficient, yada, 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 up to ap, which is the last column of A, times xp, which is some coefficient, equals y. So all this stuff about linear dependence, linear independence is related to whether or not a system of equations will have a solution. So again, restating this. If I take the matrix A and I append Y to the last column, and I check the rank of this augmented matrix, if the rank of this augmented matrix is equal to the rank of A, that means Y has to be linearly dependent on the columns of A, and therefore you can write Y as a linear combination of the columns of A, and whatever the coefficients are in this linear combination has to be the solution. So therefore it has to have a solution. All right, some additional concepts here we're going to talk about related to whether systems have solutions. So if I have an n by n matrix A, it is called non-singular if the rank of A equals n. So if the rank of this n by n square matrix equals the number of rows or the number of columns, then it's non-singular. If this is not true, if the rank of A is less than n, then we call it singular. And a square matrix has an inverse if and only if it is non-singular. So if the matrix is non-singular, that means it has an inverse. In other words, saying a matrix is non-singular is the same thing as saying that it has an inverse. Okay. When we have a square matrix and its rank is n, that means it's non-singular, then there's always a solution to AX equals Y. And if we just think for a second what that solution is, if the rank is A, then it's non-singular, and therefore it has an inverse. And if we just multiply on the left side of both sides of the equation, you get A inverse AX equals A inverse Y. The A inverse will cancel with the A or become the identity matrix. And on the right side, you have A inverse Y. So if you have a square matrix that's non-singular, and you write down a system of equation, it's always going to have a solution, and that solution is just the inverse of that matrix times the vector on the right. Okay, another way of seeing this is to use this theorem that we wrote down at the top. So if you have a square matrix A and its rank is n, if you append Y to the end, then its rank can't go down if you add another vector to the set of vectors, another column to the set of columns. So the rank of AY has to be greater than or equal to n, because we said that it was n, the rank of A is n. So if you add a column, it has to, it can't get smaller, so it has to be bigger than or equal to n. But we also know that the rank of AY has to be less than or equal to n, and that's because if we append Y to the n, we haven't increased the number of rows, which is n. And we said before that the rank of a matrix is less than or equal to the minimum of the number of rows and the number of columns. The number of rows is n, the number of columns is n plus 1, and so the rank of AY has to be less than or equal to n. So we know it's bigger than or equal to n, and it's less than or equal to n, and therefore its rank has to be equal to n. So that means, according to our theorem, then it's consistent and it has a solution. And here again, I'm just restating that you could just multiply on the left by the inverse. Now, when the rank of A is less than n, or even more complicated, when A is not square, when we're working a rectangular non-square matrix, we need something called a generalized inverse. And so we'll talk more about that later in the course. All right, so back to talking about our systems of equations. So if we have a system of equation ax equals y, this also defines a transformation from a point x to a point y. So let's just look at a simple case where A is a square 2 by 2 matrix, and x is the point 2, 1, and y is the and if you multiply A times x, you'll get y is 4 minus 1. So we start with the vector x, we multiply it by A, and we get the point y. So we're going back to this geometric interpretation of vectors and matrices. So we say that A is a transformation of x. All that means is we take x as the input, we multiply it by A, and we get a new vector y. Now this is called a linear transformation, and the reason it's called a linear transformation is because it obeys what's called the linearity property. What the linearity property says, if I have a function of x1 plus x2, it's equal to the function of x1 plus the function of x2. There's lots of things that obey the linearity property. One of them is the expectation operator. So if you have two random variables, u and v, expectation of u plus v equals expectation of u plus expectation of v. So a times x1 x2 equals a times x1 plus a times x2. So that's just to say what we mean by the term linear transformation. All right, so another extremely important topic for this course is the idea of a projection. Now, a projection, to start off with, is just a special kind of linear transformation. And here's how it works. Suppose that we have V, which is a subspace of Rn, and you have some vector y, which is an element of Rn, a vector with n elements, which are all real numbers. And here's the problem. We want to find a y hat, which is part of this subspace. So V is a subset of Rn, such that y hat is as close as possible to y. And what do I mean by as close as possible? I mean, what is the length of the vector that connects y hat and y? So, this is the equation. Remember, we can write the length as square root of vector transpose vector. So just to restate this, I'm starting with the vector y, and I'm also giving a subset of Rn, v, so a set of vectors. Y is not necessarily in this subset, but we want to find the element of that subset v that's as close as possible to the vector y, and we're calling that element y hat. So here's an example. We start with y, which is the vector 4, 1. So that's this vector here. And I'm giving you a subspace, which is the span of the vector 1, 1. And remember, so the vector 1, 1 is this point here. And remember, we can visualize or think about the span of a single vector by just taking that vector and extending it infinitely in both directions. So this dotted line you can think of as the subspace V. It's any multiple of the vector 1, 1. So the challenge is here, I want to find the vector y hat on this dotted line that's as close as possible to y, the input vector. So it's going to be this vector. So what a projection does is it finds that vector. So remember, we can think of this this linear transformation is I take an input vector y, I pass it through the transformation, and I get a new vector y hat. And what a projection does is it picks the vector y hat that's as close as possible to y. So that's what a projection is. And so to find this projection y hat, we compute the projection of y onto V, the vector space, the subspace. All right, so how do we do this? We'll come back to that. But first of all, how do we spot a projection in the wild? So what I said is a projection is a special kind of linear transformation. That means we can write it as P times y for some matrix P. Remember, y is our input vector, and linear transformations you can write as matrix times y. So we can express the projection onto the subspace as P times y equals y hat. So this linear transformation Py is a projection if and only if this matrix P is symmetric and idempotent. It also has to be square, but that's implied by symmetric. All right, what does this mean? So we already told you what symmetric means. That means if you take the transpose, you get the same matrix back. But a matrix P is idempotent if P times P equals P. Okay, so that's kind of a weird property. And if you think about it, this isn't going to be true of most matrices, that if you multiply it by itself, you get the matrix back. Okay, so why is idempotent the right property? Let's think about this problem. So we're setting this up as we start with some arbitrary vector y that's in Rn, but not necessarily in the subspace. What if we started with y hat, which is a member of the subspace V, and I compute the projection P times y hat? Now let's think back to what is this projection operator doing? You start with an input vector. Here I'm starting with y hat now. And I'm finding the element of the subspace that's as close as possible to the input vector. Now in this case, the input vector is in the subspace, and therefore the closest vector to y hat is going to be y hat itself. So I'm going to go through these equations in a second, but what I should get, if this is really a projection, is I'm going to get y hat back if I start with an element in the subspace. Then the closest one, obviously, to that one is itself. So let's see how this works. P times y hat. This is going to be P times y. So I'm just plugging in y hat equals py. And then if I group the parentheses around P times P, if this idempotent property holds, then P times P equals P, and we get Py equals y hat. So if it's really a projection, you start with an element of the subspace, you should get it back. And idempotent is the right property that makes this second equation be true. Okay, now we said what a projection is, but what is the subspace that you're projecting onto? So P is a projection matrix, then Py is a projection onto the subspace spanned by the columns of P. Now if you think about how matrix multiplication works, if you do P times y, you're going to get the first column of P times the first element of y, plus the second column of P times the second element of y. So you're going to get a linear combination of the columns of P, and therefore Py has to be in the column space of P. Let's look at some examples to make this more concrete. All right, I'm going to give you a matrix P. It's 1/2 minus 1/2 minus 1/2 1/2. And we want to check that this is a projection matrix. So what I need to check that it's symmetric and it's idempotent. Now this matrix is symmetric because the 2, 1 entry equals the 1, 2 entry, so it passes that test. To check that it's idempotent, I need to multiply it by itself. So let's do that matrix multiplication. So 1/2 times 1/2 is 1/4. And then minus 1/2 times minus 1/2 is also a fourth. You add them up, you get a half. Minus 1/2 times 1/2 is minus a fourth. Plus 1/2 times minus a half is again minus a fourth, so you get this. 1/2 times minus a half is a minus a fourth, plus minus a half times oh, I have a typo here. This should be plus 1/2. So this should be 1/2 times minus a half is minus a half, plus minus 1/2 times plus 1/2 is again minus a half. And now we get minus a half times minus a half is a fourth, and 1/2 times plus 1/2 is a fourth. Add them up, you get a half. Okay, so look what we got here on the right side. This is P again, and therefore the matrix is idempotent. Now let's apply this projection to a couple of vectors to see how this works. Now the first thing I want to do is I want to look at the matrix P and see what its columns are, because I know that P is going to be a projection onto the column space of P. So the first column is 1/2 minus 1/2, which is going to be 1/2 minus 1/2. So it's this point along the dotted line. And the second column is minus a half 1/2, which is also along this line. So the column space is the span of these two vectors, which are just multiples of one another. So it's this anti-diagonal dotted line here. So what should happen is we take a vector that's not on this anti-diagonal dotted line, do the projection, and then you're going to get a vector that is on the dotted line. So let's see how this works. Let's start with the vector 4, 1. So that's this point here. It's not on the dotted line. And then we're just going to guess the closest point to here, 4, 1, along the dotted line is going to be somewhere around here. So let's see what happens. So 1/2 times 4 is 2. Minus a half times 1 gives us 3/2. Minus a half times 4 is minus 2. Plus 1/2 times 1 gives us minus 3/2. And that's going to be 1.5 minus 1.5. So you get this point here. Let's do another one. This point minus 2, 3 is closer to the dotted line. So we're going to get something over here. We do 1/2 times minus 2, we get minus 1. Minus 1/2 times 3, we get minus 5/2. Minus a half times 2 is 1. Plus 1/2 times 3 is 1.5. Add those up, you get 5/2. So this point here is minus 2.5 plus 2.5. So we get something right on the dotted line. And this is like, if you think about this, this is almost like magic. This is really cool. And it turns out that projections are going to be the secret sauce of linear regression. So when you do a regression, what you're really doing to get what's called the fitted values are you're projecting the data onto this column space of the covariates. So just a few more facts about projections. If we have a projection matrix P, which is symmetric and idempotent, I minus P is also a projection. So again, what do we need to check? We need to check that it's symmetric. So that if you take the transpose of I minus P, you get transpose of I, which is I, minus the transpose of P, which has to be P because P is a projection. Next thing we need to do is multiply them together. So if we do I minus P times I minus P and we FOIL it, we get I times I, which is I. I times minus P is minus P. Minus P times I is minus P. And minus P times minus P is plus P times P. Now this P times P is going to be equal to P. So we get I minus P plus P. Two of them cancel and you get I minus P. So it's also idempotent. And that means I minus P is a projection. So if we take our example from above, where p was 1/2 minus 1/2 minus 1/2 1/2, and we do I minus p, so we're going to get 1 minus 1/2 is 1/2, 0 minus 1/2 is 1/2, 0 minus 1/2 is 1/2, and 1 minus 1/2 is 1/2. So this is I minus p. And we think about what is the column space here. Well, this is just going to be the diagonal line now, because this is 1/2 1/2 is on the diagonal, and so is 1/2 1/2, of course. So the column space of I minus p is this diagonal line. All right, another important projection for linear regression is 1 over n times j. Remember, the definition of j is you take the 1 vector, so this is a column vector of 1s, and multiply it by its transpose. So let's check. So this is obviously going to be symmetric. This is just a matrix of 1, so it's a symmetric matrix. If you want to see here, if you take the transpose of the product of two matrices, you get the transpose of the second one times the first one transpose. So transpose of 1 transpose is 1, and 1 transpose is 1 transpose, so you get this back. So let's check that it's idempotent now. So if you do 1 over n times j times 1 over n times j, you can factor out the 1 over n's, you get 1 over n squared. And then plugging in the definition for j, you get this. And if I just do the middle multiplication first, you'd have 1 transpose times 1. So we're taking a row vector of 1s and multiplying it by a column vector of 1s. That's just the dot product of the 1 vector with itself. So you get 1 times 1 plus 1 times 1 plus 1 times 1 n times. So that has to be equal to n. So this middle thing is going to be n. It's going to cancel with this one. Oh, that's what this equation does. And you get 1 over n, 1 transpose. So it is idempotent as well. Now, what kind of projection is this? We're going to give kind of a qualitative description here. If I take a vector y and pass it through the projection, what do I get? I get, let's do it this way. We can rearrange things. So 1 times parentheses 1 over n, 1 transpose y. Now 1 over n, 1 transpose y, let's think about what that is. 1 transpose y is the dot product of the 1 vector with y. So you get 1 times y1 plus 1 times y2 all the way up to 1 times yn. That's just the sum of the entries of y. And if you divide by n, that's just the average. So this is going to be the 1 vector times the scalar equal to the average of the y vector. And so you're going to get 1 times the average, 1 times the average, 1 times the average, and you just get a vector of the averages. So we say that this projection, 1 over nj, projects to the average. And the column space is the span of 1, because every column is equal to the 1 vector. And y bar is the point in the span of 1 that is closest to y. Now, if you think about this, this is kind of cool, actually. So if we take any element that's in the span of the 1 vector, we can write it as just a vector of the same number repeated over and over again. So remember, the span of a vector is all the vectors that can be written as a scalar coefficient times that vector. So if you have c times 1 vector, it's equal to c. So we'll call that vector c. And if we look at any such vector c, where all the entries are the same, and look at the squared length of that vector, you get this. And this is equal to the sum yi minus c squared. And what this projection is doing, it's projecting onto this space, the span of 1, and it's finding the point in that span that's closest to yi. And it turns out when you do this projection, you get this y bar vector. So therefore, if you pick any c, the best possible choice in terms of its distance to the vector y is going to be the average. So you've probably seen this before, that the average minimizes this sum of squares. And this is why it minimizes that sum of squares from a geometric linear algebra standpoint. That if you take the one vector, so if you take the J matrix, it's a projection onto the vector of ones. And so if you take any point y, the closest point to that is just the average vector, the closest point in that subspace. And just like before, if we do I minus the projection matrix, this is also a projection. This is also an interesting one that we'll talk more about. Now we come to eigenvalues and eigenvectors. Now, we're only going to be talking about eigenvalues and eigenvectors for certain types of matrices. And those certain types of matrices are real. That just means that all the entries of the matrix are real numbers. Symmetric matrices, which we've already talked about, that just means that if you have a matrix A, it equals A transpose. And non-negative definite matrices. So let's take a minute and talk about what we mean by non-negative definite. So if we have a matrix capital A, it is non-negative definite if the following is true for every vector x. So if we have a vector x and we do x transpose AX, that this quantity is bigger than or equal to 0 for any x. This quantity, since x is a column vector, this is a 1 by n times an n by n times an n by 1. So this x transpose AX is a scalar. And non-negative definite means that this scalar is bigger than or equal to 0 for every vector x. A related concept is positive definite. That's the exact same thing, except we're requiring that x transpose AX is bigger than 0, strictly bigger than 0, whenever x is not the 0 vector. So the first time you see this criterion, x transpose AX is bigger than or equal to 0 for every x, no matter which x you pick, this seems like, how could this even be possible that you could find a matrix such that this is true? But you can, and here's a couple of simple examples that are positive definite. So the first one is the identity matrix, the n by n identity matrix. If we take an arbitrary vector x and do x transpose IX, well, IX is just equal to x, so this becomes x transpose x. And x transpose x is just the sum of the squared entries. So you're going to get x1 times x1 plus x2 times x2, so on and so forth, up to n. So it's the sum of these squared entries. If you square a number, it has to be bigger than or equal to 0. And so this sum is going to be bigger than 0, which shows that In is positive definite. Another matrix that you've seen is Jn. So you do x transpose Jnx. Remember, the definition of Jn is it's the one vector times the one vector transpose. So if you do x transpose 1 times 1 transpose x, and you collect things in this way, so you do this multiplication first, and then you multiply it by this. Each of these two quantities inside parentheses are scalars. So x transpose 1 is a vector, it's just the dot product of x and 1. And this is also the dot product of x and 1. Now the dot product of x and 1 is just the sum of the entries, and we're multiplying that by itself. So this is just the sum of the entries squared, which also is the square of something, so it has to be bigger than 0. All right, now we come to our definition of eigenvectors and eigenvalues. If you have a matrix A, real, symmetric, non-negative definite, and multiply it by some vector z, if you get back a scalar, lambda, times the same vector, then we say that z is an eigenvector of A, and lambda is the corresponding eigenvalue. Now, before we go on any further, there is some ambiguity here because suppose z is an eigenvector for a. And then we do a times, just as an example, 3 times z. Well, this is going to be, we can pull the 3 out, and you get 3 times az. Since z is an eigenvector for a, the az becomes lambda z, and you get lambda times 3z. So here, z is an eigenvector, but so is 3z, because you can do a times 3z, you get lambda times 3z. So we're going to use the convention that the length of z has to be 1. So if you do z transpose z, which is also the length of z, that has to be 1. Then you can't, if you multiply it by something, the length is no longer 1. So now you have these distinct eigenvectors that you can't multiply by anything. All right. So an n by n matrix, real, symmetric, non-negative, definite, has n real, non-negative eigenvalues and n corresponding eigenvectors. The notation we're going to use for these eigenvalues and eigenvectors are lambda 1 up to lambda n, and the eigenvectors z1 up to zn. I get tired of writing underlines here, so I'm going to leave the z's just as z's without underlines, but remember that these are going to be vectors. So A is an n by n matrix. It has n real eigenvalues and n eigenvectors. All right, so if you do zi transpose a zi, let's see what happens there. The a zi becomes lambda zi. Lambda, this should be a lambda I, sorry. If you pull out the lambda I, you get lambda I zi transpose zi, and you get lambda. So one way to think about the eigenvalues is this is what you get when you do zi transpose a zi. Now, this thing lambda, this is why lambda has to be a non-negative number, because a was non-negative definite, which means that if you take any vector, which includes the ith eigenvector, you're going to get a number that's bigger than or equal to 0. So this shows that lambda I has to be bigger than 0 for every I. All right, now let's work out another important property of eigenvectors. Suppose we take 2 of those n eigenvalues, and for this demonstration here, we're going to require that those 2 eigenvalues, lambda I and lambda j, are not equal. We'll do the case where they're equal in just a second. So if I do zi transpose a zj, this becomes zi transpose lambda j zj, and you can pull the lambda out and you get lambda j zi transpose zj. Now let's do the same thing except flip I and j. So here we're doing zj transpose a zi. First of all, let's remember that if we took the so first of all, this is a scalar. Both of these are scalars because that's a 1 by n, n by n, and an n by 1. If we were to think of this as a 1 by 1 matrix and we take the transpose of it, we would get zi transpose a transpose, which is a because a is symmetric, times zj, which is the same as this up here. So these two expressions are exactly the same, which is why if you're peeking ahead, what we're going to do is we're going to take the difference of these, and so the difference is going to be 0. But let's move along with this equation. So this becomes lambda I zi, so it's zj transpose times lambda I zi. Pull out the lambda I, you get lambda I times zj transpose zi. Now, if you look at this expression here, these two numbers are the same. So zi transpose zj is just the dot product of zi and zj. And zj transpose zi is just the same thing, the dot product of zj and zi. So let's take the difference between these two equations. Here we said we're going to get 0. So this is 0. If we take the difference between these two, we get lambda j minus lambda I times that dot product. That's taking the difference between these two, recognizing that zi transpose zj equals zj transpose zi. So we get 0 equals lambda j minus lambda I times zj transpose zi. So that means that one of these two quantities on the right, either lambda j minus lambda I or zj transpose times zi, has to be 0. Now we started with the assumption that lambda I was not equal to lambda a, so we know that the first quantity is not 0. So that means the second quantity has to be 0. So zj transpose zi equals 0. So if you take the dot product of zi and zj, you get 0. Now when two vectors satisfy this property, x transpose y equals 0, we say that these two vectors are orthogonal. So that's another definition for us. So if we have two eigenvectors with two different eigenvalues, those two eigenvectors have to be orthogonal. So the result of this is going to be the eigenvectors of real symmetric non-negative definite matrix are orthogonal. Now we skipped a case that we're going to come back to. What if we have two of the same eigenvalues? So if lambda I equals lambda j for some I not equal to j, then the eigenvectors zi and zj need not be orthogonal. At least this argument doesn't prove that they are orthogonal because we started with the assumption that the two eigenvalues were different. Okay, so let's follow this through. What we're going to show is that we can find two different eigenvectors, zi star and zj star, that are still eigenvectors of A, but that are orthogonal to one another. So let's see how this works and why this works out. So if we do A zi, we get lambda I zi. If we do A zj, we get lambda j zj, but we said that lambda I equals lambda j. So if we do A zj, we really get lambda I zj, which means that if you do A times the sum of zi plus zj, you're going to get lambda I times zi plus zj. Now this means that zi plus zj is an eigenvector for A. Now if you're worried about the fact that we made the assumption that the zi's had length 1, you could always scale this by whatever you need to scale it by to make sure that this has length 1. Because in fact, it turns out that AZI plus BZJ is an eigenvector for A for any two scalars. So if you take any linear combination of ZI and ZJ, that turns out to be an eigenvector for A. And its eigenvalue is going to be lambda I. So this gives us a clue about how we can modify these two eigenvectors and get two eigenvectors that are orthogonal. So here's a constructive way to do it. So if we define zi star equal to zi, and then zj star equal to zj minus zi transpose zj times zi, then these are both going to be eigenvectors for A with eigenvalue lambda I. You can check that yourself. Of course, this is going to be because it started with 1, but this is also going to be because it has this form of BZJ plus AZI, because this is a scalar. So I'll leave it as an exercise for you to show that ZI star and ZJ star are orthogonal. So this means we can always find for any real symmetric non-negative definite matrix A, we can always find a set of orthogonal eigenvectors, even if some of the eigenvalues are repeated. All right, now we come to the eigendecomposition. So this is just restating that. If A is real, symmetric, non-negative, definite, we can always find these, what I'm calling mutually orthogonal set of eigenvectors, z1 to zn. By mutually orthogonal, I just mean if you take any pair of eigenvectors, zi and zj, those are orthogonal. So let's collect all of these eigenvectors, z1 to zn, into an n by n matrix that we'll call capital Z. So I'm going to write capital Z in block form, where the first column is z1, the second column is z2, and then the last column is zn. If we were to do Z transpose Z, we would get, in the ij entry of that matrix, we're going to get Zi transpose Zj. You can check this yourself by writing down Z transpose in block form. You're going to write it as Z1 transpose, and then below that Z2 transpose, and all the way down to Zn transpose. So if you do this, you'll get, in the ij entry of Z transpose Z, you're going to get Zi transpose Zj. And this is 1 if I equals j, because these all have length 1. And it's 0 if I is not equal to j, which is true because these are orthogonal. So this is just the definition of what the identity matrix is. Identity matrix is 1 if you're on the diagonal, I equals j, and it's 0 if you're not on the diagonal. So Z transpose Z is the identity matrix. Now what is true, if you take a matrix and you multiply it by another matrix and get the identity matrix, then that matrix has to be the inverse. So in this case, the inverse of Z is its transpose. And this is the definition of what's called an orthogonal matrix. A matrix Z is orthogonal if its inverse is equal to its transpose. Okay, now this is going to be an important property that we're going to use in the eigendecomposition of A. So let's look at this matrix multiplication, A times Z. So A is our real, symmetric, non-negative, definite matrix. Z is the matrix that contains its eigenvectors. So, and we're going to do the matrix multiplication A times Z. All right, so if we do this in block form, we get AZ1 in the first column. The second column is going to be AZ2, and then all the way up to the last column is going to be AZN. So each of these is an n by 1 vector. And we know that AZ1 is just lambda 1 Z1. AZ2 is lambda 2 Z2, all the way up to AZN is lambda n Zn. So these again are column vectors that we're writing in block form. And then let's do Z transpose AZ. So we'll take this thing and do Z transpose on the left. This is what Z transpose looks like in block form. And we just worked out that this is A times Z. And so if we collect all these matrix multiplications, you get lambda, the 1, 1 entry is going to be lambda 1 Z1 transpose Z1, all the way down. This N1 entry is going to be Zn transpose lambda 1 Z1, so you get this. The 1n entry is going to be Z1 transpose lambda n Zn, so you get this. And this is the nn entry. Now, if you look at the entries of this matrix, this one is going to be lambda 1 because Z1 transpose Z1 is 1. This one is going to be 0 because Zn transpose Z1 is 0 because they're orthogonal. So what you're going to end up getting is along the diagonals, you're going to get the eigenvalues, lambda 1, lambda 2 up to lambda n. And then off the diagonal, you're going to get zeros. So the matrix is going to look like this. So this is my notation for writing down a diagonal matrix. I'm just listing what the values are on the diagonal, and then off the diagonal, I'm just putting a big 0. So this, again, is an n by n matrix, but I'm writing it in shorthand. This matrix, let's just call it D. I'm calling it D for diagonal. So D is defined as Z transpose A Z. If we were to calculate Z times D times Z transpose, we get Z transpose A Z times Z transpose. If we collect the multiplications here and do Z transpose times A times Z transpose, this is just A, because Z transpose is the inverse of Z, so this becomes the identity. And the same thing here, this becomes the identity. So it's I, which is A. And this representation for A, so what we found is we have A here, and we can write it as ZD transpose, where Z are the matrix of eigenvectors, and D is the diagonal matrix of eigenvalues. So this representation for A as the product of these three matrices is called the eigendecomposition of A. And for obvious reasons, it's because it's constructed out of eigenvectors and eigenvalues. And it's also sometimes called the spectral decomposition. Now let's apply these ideas of the eigendecomposition or the eigenvalue decomposition to the projection matrix. So let's say that capital A is a symmetric and idempotent matrix, i.e. it's a projection matrix. And just to restate what that means is if we do A times a vector x, this projects the vector x onto the column space of A, or in other words, it finds the vector in the column space of A, or the span of the columns of A, that's closest to the input vector x. So A, its columns define a subspace. And let's define also a set of vectors z1 up to zp to be an orthogonal basis for the column space of A. What that means is if you take the span of z1 up to zp, it defines a subspace that's equal to the span of the columns of A. Additionally, these vectors z1 to zp are mutually orthogonal, and they're also, let's say they're also orthonormal, meaning their length is 1 and they're all orthogonal to one another. Further, let's define the n by p matrix capital Z to be a matrix whose ith column is zi. So there's p of these, each has length n, therefore it's an n by p matrix. A, again, is an n by n matrix. And our claim here is that the matrix A, our projection matrix, can be written as capital Z times capital Z transpose. Therefore, the eigendecomposition of A is the following. So this thing here, block matrix ZU, are the eigenvectors of A. The thing in the middle are the eigenvalues of A, and then this is just ZU transpose. So we've already defined what Z is. That's just this matrix. U it can actually be any n by n minus p matrix whose columns are mutually orthogonal to themselves and to Z. That makes this whole matrix an orthogonal matrix. It actually doesn't matter. As long as the columns of U satisfy that property, it actually doesn't matter what they are, because they end up multiplied by 0 anyway when you pass it through this matrix multiplication. So the important point here is that you have the matrix Z as part of the eigendecomposition, and the eigenvalues corresponding to these eigenvectors in Z are all 1, and then the other eigenvalues are all 0. So let's give a proof of this claim. If you look at the matrix ZZ transpose, it's pretty easy to verify that this is a symmetric and idempotent matrix. So let's do symmetric first. If you do the transpose of ZZ transpose, well, you do Z transpose transpose is Z, and then Z transpose. So this thing on the right is equal to this, so it's symmetric. To check whether it's idempotent, you multiply ZZ transpose by itself, ZZ transpose. And if you cordon off the multiplication to do this middle multiplication first, Z transpose Z, remember that the columns of Z are orthogonal. So if you do Z transpose Z, you get the P by P identity matrix. And then you either multiply Z by that or that by Z transpose, and it goes away, and you're left with ZZ transpose. So here we just showed that ZZ transpose times ZZ transpose equals ZZ transpose, and therefore it's idempotent. So that means that ZZ transpose itself is a projection matrix. So to complete the proof, we're going to think about what is the space that ZZ transpose projects onto. Well, if you think about the column span, this is the same thing as the column span of Z. I don't have the step here, but so suppose you take any input vector x and you cordon out the multiplication as Z transpose times x, so you get a new vector, let's call that y. This just becomes Z times y, which is clearly in the column span of Z because it's just going to be a linear combination of the columns of Z when you write it out that way. So the column span of ZZ transpose is the same as the column span of Z. And we set up Z so that it is the column span of Z is the same as the column span of A. Remember back to the definition, we said that this set of vectors is an orthogonal basis for the column space of A. So the column space of Z equals the column space of A. Therefore, if you do this multiplication, ZZ transpose times X, and compare it to A times X, these are both projections onto the same column space. And so they should give the same answer. So that means that ZZ transpose times X projects to the point in the column span of Z or A that's closest to X. And this does the same thing. So these have to project to the same point. And you'll notice that it doesn't matter what X is. So this is true no matter which X you plug in. So that's why I say for arbitrary, or I have a typo here, arbitrary vector X, because they both project onto the same vector space. So if you play a little game and say, well, if I stack a bunch of X's together and make it the identity matrix, so what I mean by that is the first column of ZZ transpose times the identity matrix is just ZZ transpose times X, where the first entry of X is 1 and the rest are zeros. And then the second column of the matrix multiplication is 1 where X is 1 in the second entry, so on and so forth. So if you do this matrix multiplication, since this is just a bunch of matrix vector multiplications stacked together, and we said that these give the same answer, then these two matrices should be equal as well. But then if you just do the multiplication, you get ZZ transpose equals A because the identity matrix goes away. And therefore, we've completed our proof that ZZ transpose is equal to A. Okay, so this is a kind of a powerful thing because one of the main reasons is it tells you something about the eigenvalues of a projection matrix. The eigenvalues of a projection matrix are either 0 or 1, and the number of eigenvalues that are 1 is equal to the dimension of the span of A. So we set this thing up so that this is an orthogonal basis for the column space of A, and there are P of them. And this turns out to be IP here. So this is this is an important theorem because it tells us something about the eigenvalues of the projection matrix. Okay, so immediately we can get kind of an interesting corollary. So if we have a symmetric idempotent A, in other words, if A is a projection matrix, then its rank is equal to its trace. Okay, so why is that true? So if we just say that the rank of A is equal to P, that means we can find a basis Z1 to ZP, orthogonal basis that spans that space. P just happens to be equal to the trace of IP. That's just a kind of a simple statement. The trace of a P by P identity matrix is equal to P. But it turns out that IP is equal to Z transpose Z, just because Z transpose Z is Z. So it's just because Z is an orthogonal matrix. And the trace operator has this property that you can permute the matrices and the multiplication cyclically. So you can take this Z and move it to the other side. Recall that it's not necessarily true that Z transpose Z equals Z transpose, but it is true that the trace of Z transpose Z equals the trace of Z transpose. And in this case, we just showed that ZZ transpose equals A. So therefore, the trace of A, if you go back through all these equal signs, is equal to the rank of A. So that's this is going to be a useful property when we go to figure out properties of sampling distribution of the variance estimator.